dear students. Today my topic is UV spectroscopy from applied chemistry 4th year. It's the remaining part of my last lecture. In my last lecture I have told you about what is the spectroscopy and what is the absorption of ultraviolet visible radiations, and I have already explained about the electromagnetic spectrum. So UV radiation, which is the part of electromagnetic spectrum, ranges from 200 nanometer to 800 nanometer. I have already explained that ultraviolet and visible radiations interacts with matter, which causes the electronic transition, means promotion of electrons from the ground state to higher energy state. And higher energy states and the forming transitions, pi to pi stars transition and to pi stars transition, sigma to sigma stars transitions, results after the interaction of light UV radiation with matter. Today I will discuss the quantitative analysis of unknown concentration. It means Lambert-Beer's law. I will explain the instrumentations of the UV absorption. So, first of all, look at this simply drawing about the UV absorption spectroscopy. Here is the first is the light source. Look at this light source, monochromator, and then reference cells, sample cells, and detector. First of all, this is the light source. You can select the light, any bulb light, any white light, electromagnetic radiations. This is called as the polychromatic radiation. It consists of all the wavelength, depends upon the specific wavelengths. When you passes this light through the monochromator is the part of your spectrophotometer, that part which converts the polychromatic radiations into the monochromatic rays. It means this light passes through the monochromator, prism, or grating, anything else, and convert into the specific wavelength. Here my topic is the UV absorptions, UV range. So it selects the particular wavelength rays. Monochromator convert the polychromatic radiation into the rays of the particular wavelength of UV range. This particular wavelength, then here is the chopper or splitter. This divide this rays into two parts. Divide it into two parts. These rays are of the same intensity, which one of them is passes through the reference cell, other is passes through the sample, which both of the rays transmitted from the reference cell and the sample cells are detected by the detector. This is all about the drawing. This is all about the spectrophotometer theme. Now, I have already told you. I look at there two coverts, two parts. Here is written reference cells, or other is written the sample cell. When you fall the UV radiations on the reference cells, for example, I consider here is the water or non-absorbing species. Here is the water non-absorbing species. When the UV radiations, when the light particular wavelength falls on the reference cell, there is no absorptions, and the light after reflections come as a transmitted light, and detect this transmitted light. The incident light, intensity of incident light, that I called it I naught, and when fall on the reference cells and after the reflection, the transmitted light, which I called I, they are the same. There is no loss, there is no absorptions, there is no loss of intensity. It means the intensity of the radiation at the start is the same. The intensity of the radiation at that. My dear students, try to understand. If light of particular wavelength falls and there is no absorption, there is no transitions, then the intensity of the transmitted light is 100%. There is no loss, there is no little bit loss. Same radiations after splitting with the particular wavelength fall on the sample. This is called as the I naught. No, there is a sample, there is a particular molecule which absorbs the radiations. Due to this absorptions, intensity is little bit lost. No detector detect the light. It has the less intensity as compared to intensity, as compared to the sample, as compared to the reference cells. So that this intensity is If there is a sample, so we fall light, there is absorption. And transmitted light is always less than the incident light. There is a net change between the I to I naught or I naught. And this is the detector. The detector always detects the transmitted light, particularly transmitted light. But when we are and try to measure the graphs and the concentration of the unknown sample, there is a problem. There is a difficult, because transmittance and absorbance are quite different to each other. They are different to each other. So if we have to draw a graph for the transmittance and the concentration, there is a slope. There is no linear relationship. So to make the linear relationship, we need a absorbance, not a transmittance. So always for taking the absorbance, to change the transmittance into the absorbance, we take the log. Here is the law that is called as the Lambert's law, Lambert-Beer's law. There is a combination of the two laws, Lambert's law and the Beer's law. Here I have told you there is a transmission in the reference cell. There is 100% transmitted light has an intensity I over I naught. But if we have to take absorbance is always the inverse of transmittance. A is equal to 1 by T. So if we want to take the linear relationship between the concentration and the absorbance, we have to take always to convert the slope value into the linear relationship, we need a log. So the value of log absorbance is equal to log value 1 by T, and log T is I over I naught. And when you have to change 1 by T, here is absorbance is log I naught over I. Next is the Lambert's Beer law. Lambert says absorbance of the light in homogeneous solution is directly proportional to the length of the sample, and the Beer state absorbance of the light in a homogeneous solution is directly proportional to the concentration of the sample. So Lambert's law. Absorbance is E log value of I naught over I is equal to E. A is called the epsilon molar extension coefficients, and L is the length. So two things are important. One shows the Lambert, other shows the Beer's. Lambert says the concentration, the absorbance is directly proportional to the path length, means the path length of the covert or sample holder. Covert is called as the sample holder. And the Beer says the absorbance is directly proportional to the concentration. By combining these two laws, so absorbance is A is equal to ECL. E molar extension coefficient, which is the log value of transmittance. Transmittance is I naught over I. So this is all about Lambert-Beer law. A is equal to ECL. Absorbance is directly proportional to the concentration and path length of the covert cell. It means if there is more concentration, there is more absorption and less transmittance. If there is less concentration, less absorption and the more transmittance. So try to understand, girls, if there is less absorption, transmittance is more. If there is more absorptions, concentration is more, absorption is more, and the result, the transmittance is the less. Here's the graphical representation. That is very important. I have told you, this first graph is, that is the concentration and the percentage transmittance. If there is, look at this concentration. If there is concentration, there is a slope. If there is less concentration, less absorption, and the more transmittance, that is 100%. As we go down, then the transmittance is decreases. It means absorption is increases. So this slope, if I want to measure the concentration of the unknown sample, it will not be possible. Linear relationship is the best to measure the concentration of the unknown sample. What will I do? I convert this transmittance into the absorbance by taking the log of T. Here is the linear relationship. Absorbance, more concentration, more absorbance, less concentration, less absorbance, and linear concentration. Here you can easily put here, for example, here you are, if you want to measure the concentration of unknown sample, you can easily sort out the concentration of the sample. So this is very important. So Lambert's-Beer law says absorbance directly proportional to the concentration and path length, This is the third one graph, lambda max. What is the lambda max? The molecule, each particular molecule shows the maximum absorption on the particular wavelength. This particular wavelength for which the molecule or a compound shows maximum absorptions is called as the lambda max. This is the qualitative analysis. If you want to determine the unknown compound, you can easily check it from the lambda max. Here is the concentration. If you want to know if you want to determine the unknown concentration by using the Lambert-Peier's law, you can easily sort it out the unknown concentration of the sample. This is called as the quantitative analysis. Second most important here is the topic chromophore. This is all about the UV visible spectroscopy. There are some terms which are used in the UV spectroscopy. One is the chromophore. Chromo means color. Chromophore means a particular compound which imparts the color is called as imparts the particular color to the solution is called as the chromophore. And what is the chromophore? Chromophore is basically the ethylene, acetylene, these double bond or conjugations, acetylene, where the N to pi star transitions and pi to pi star transitions are present, shifts the wavelength to longer wavelength is called as the chromophore. And oxochromophore are those compounds or a group or a molecule which are not itself chromophore, which not really, but it imparts and help the chromophore to increase its absorption. It's very simple example is that if as there is OH, I have given you example of benzene. Benzene's lambda max is 255, but if there is a phenol, OH is not a individually a chromophore, but when it attaches the benzene, makes the phenol, then OH increase the conjugation. By increasing the conjugations, the lambda max shifts to 270 nanometer. So this is called the oxochromophore, which are not a chromophore but supports the chromophore to absorb on a particular longer wavelength. These are the terms used. The difference between the chromophore and oxochromophore. Chromophore itself imparts color and shifts the wavelength or absorption to the longer wavelength. Oxochromophore or chrome is not a particular chromophore but supports the chromophore. You can say just like a phenol has the lambda max 270 nanometer, but the benzene has the 250 nanometer. OH group individual is not supporting, but when there is two effects, bathochromic effect and hypsochromic effect. Bathochromic, look at this picture. Bathochromic shift means the shift if some molecule or a solvent effect shifts the wavelength or lambda max to the longer wavelength due to the conjugations or due to the any reason, this shift is called the bathochromic shift. As I have told you in the last example, benzene has the 250 nanometer lambda max, but if phenol, if OH group is present there, it shifts the wavelength to the 270 nanometer, a longer wavelength. This is called the red shift or bathochromic effect. Hypsochromic shift, if there is some molecule or solvent which shifts the wavelength to the shorter wavelength or a higher frequency, this is called the hypsochromic effect. If you remove in some molecule, a conjugation is removed, then the wavelength shifted to the shorter wavelength. This is called the hypsochromic shift. Here there is two representation. Above is the hyper and under is the hypochromic shift. There are two shifts. In bathochromic and hypsochromic shifts, wavelength is shifted. But in the hypochromic, and try to understand, hyper and hypo means if the intensity increased due to the any reason, is called as the hyper. If an intensity of the rays, transmitted light, is decreased, this is called as the hypochromic effect. These are the two effects which are shown here in this place. Here is the next topic is the very important topic. Next is the instrumentations. Instrumentation, I have drawn a very simple components of the instrumentation. This is the source, monochromator, sample, detector, recorder. Number one, spectrophotometer. There's two types of spectrophotometer, single beam and double beam. Single beam spectrophotometer, as I have shown you, just like a source, monochromator, and there is no reference cell, just totally the radiations fall on the cell. There is two types of the spectrophotometer, single beam and double beams. In the single beam spectrophotometer, source, monochromator, direct, sample and the detector. But in the double beam spectrometer, as I have explained, first of all the source, then there is a monochromator and splitter. Split the radiations into the two parts. One is the reference cell, sample cell, detector, amplifier, at the end amplify the rays. Here is the source of light. That is very important. Source of light, many source of light is used for the range of the UV absorption radiations. Deuterium lamp is one of them. Deuterium lamp, hydrogen lamp, and these tungsten filament lamp, all these are just like a lamp. But in this lamp, the idea of this lamp or theme of this lamp is that in this lamp a particular gas is filled with the pressure. When the current is passed, after the collision of this current and this, after the collision of this current and the already vibrated gas molecules, the result is the generation of the electromagnetic radiations which falls in the range of the UV radiation. So that is produced the UV radiation. So all the three bulbs, all the three tungsten filament lamp, deuterium hydrogen lamp, all these follows this basic idea that gas is filled with the pressure, current is passed, after the collision of these two, result generation of the electromagnetic radiation, that is the in the range of the UV region. So there are different ranges. For example, deuterium range is 160 to 375 nanometer, and tungsten filament lamp produces the UV radiation between the ranges of 350 to 3000 nanometers. So these all the source of the light produce the particular range of the UV region, and basically it looks like a bulb. Next is the monochromator. That is the monochromator. Monochromator is a whole part in which there is entrance slit and prism or grating. Number third is the exit slit. Here is the radiations, as the name indicate. Monochromator convert the wavelengths, different wavelengths, into the one rays of the particular wavelength. Here is the two types of the used. One is the prism and diffraction grating. Prism reflects the light into the, just like you have to pass the white light, it divide the light into 7 colors with a particular wavelength it shows. But there is some problem. Grating is the most focusing and most important type of the monochromator, which convert the polychromatic into the monochromator. For example, look at this picture. In the grating there are so many smart prisms or grooves, that is a smart type prism, which reflects the particular light with a particular wavelength at a particular angle. So this is very important. And third one is a splitter. Splitter is also the part of the monochromator. This splitter splits the radiations into the two parts with the same intensity. So prism, grating, entrance slit, exit slit, all are the part of the monochromator, which try to initiate the rays intensity will be remained with the same intensity throughout the whole system or whole process. Third one is the detector. There are 3 types of detector: photocells, photomultiplier tube, and the photovoltaic cells. Photomultiplier tube, this is mostly used in the UV radiations. Basically, the function of detector is to convert the radiant energy into the electrical signals, which are amplified and come in the form of the absorbance. As I have told you, when the high energy radiation or radiant energy or rays struck the photomulti detector, they convert the radiant energy into the electrical signals. How they function, how they are working, this is the photomultiplier tube in the picture. Look at this picture. Here is the photomultiplier tube. There is 2 electrodes. One is cathode. Look at the picture. One is anode. And in the diodes, in the form of the arc, you can watch, there are so many diodes. There is 9 to 18 diodes are present in this cabin. So when the radiation fall on the electrode, just like a cathode, what happened, they strike with the one dynode. Light falls on the cathode, they strike with the dynodes convert this radiations into the electrical, generate the electrons, and these electrons are multiplied with number of the dynodes. At the end of this, at the cathode, there is a collection of so many electrical so many electrons which which passes to the amplifier, and amplifier gives the electrical signals and shows the spectrum of the absorbance. The second one is the photocell. This is also on the same criteria. Here is the sensitive layer, cathode, anode, and the light falls on the cathode, and then fall on the sensitive layer, then fall on the particular sensitive layer, which convert the radiated energy into the electrical signals. These electrons, generation of electrons, these electrons which are generated, collected at the anode. Due to the difference of potentials difference, these radiation is calculated with the help of the amplifier. This is the main objective or main idea of the photocells. Second is the last is the coverts, which I have discussed, sample holders or the reference cells, reference solution holders. This is the specific type of the covert, and it's very important in this point of view. This is made up of the glass, and this is made up of the glass, but glass is not using for the UV radiation because it absorbs the UV radiations, but it is particularly formed of this particular covert is made up of the quartz. So these are easily non-transparent. It is transparent towards the UV radiation when it is made up of the quartz. Thank you. This is all about the UV spectroscopy. I have discussed what is the spectroscopy, UV absorptions, their transitions, Lambert-Beer's law, instrumentation. This is all about. In the next topic, we will discuss the another part of the electromagnetic spectrum, that is called as the IR. Thank you so much. One thing I want to clear, dear girls, I have prepared these slides myself. I have written it is not a copy paste. So if you consider it as your notes, then it will become easy for you to understand. Inshallah, we will come to the next lecture. Thank you.